Good morning and welcome to this the lecture number 20 of the course Stochastic Hydrology. If you recall, in the last lecture we were discussing the case study number 3, which is on the monthly stream flows of the Kaveri river at the KRS reservoir. Sorry. So, what we did in that case study up till now is we plotted the time series, we computed the correlogram and plotted the correlogram. We also looked at the partial autocorrelations and the power spectrum. Then we went on to build the ARMA type of models for both synthetic generation of the stream flows as well as for one time step ahead forecasting. What did we do in that? We considered several candidate models of the ARMA family. We constructed these candidate models based on the information that we obtained from the specifically from the correlogram and the partial autocorrelations, and then we considered several of these candidate models. Corresponding to each of the candidate models, we estimated the parameters by considering half the data. We had 40 years of data, which means 480 values we had for the monthly time series. We considered the first 240 values to calibrate the models. By calibration of the model, I mean estimation of the parameters. We use the Armax function of the MATLAB to estimate these parameters. You can use several of any of the other algorithms that are available in standard packages, computer packages. You can estimate the parameters associated with the ARMA models. Remember that we were working for this particular case study, we were working with the standardized flows, and then we estimated the likelihood values for each of the candidate models, picked that particular model which gives the maximum likelihood value among those models that we were considering. The model that is chosen based on the maximum likelihood value is meant for long term synthetic generation of the data, which are typically used for assessment of risks, assessment of reliability of the particular system, for fixing up the capacity of the reservoir and so on. So, for all normal purposes of planning and operational decisions that we often come across in water resources, we use the long term synthetic generation of the data. Typically, we generate for 100 years, 150 years, even 200, 300 years and so on, depending on the type of application that we are interested in. Then we also chose a particular model based on the minimum mean square error. The mean square error criteria we use for short term forecasting, and typically we are looking at short term one time step ahead forecasting. We considered both contiguous as well as non contiguous models, and for both the contiguous as well as non contiguous models, we did this exercise and picked up models corresponding to contiguous models based on the maximum likelihood criteria and the non contiguous models based on the maximum likelihood criteria, and then we compare the two. If the maximum likelihood criteria are quite close to each other, maximum likelihood values corresponding to the chosen model from the contiguous type of models and the non contiguous type of models, if the maximum likelihood values are quite close to each other, then we choose that particular model which has minimum number of parameters. So, this is the principle of parsimony. If two models are satisfying more or less the same objective, then we choose that particular model which has lower number of parameters. Similarly, for forecasting also we did the exercise both for contiguous as well as non contiguous models. And in the case of forecasting, the simplest model, namely the ARMA 10 model, for contiguous type of models and ARMA 2.0 model for the non-contiguous models. They surfaced up to be the best models in terms of the minimum in terms of the mean square error values. Okay, in today's lecture what we then do is, so we have chosen one model corresponding to the maximum likelihood value likelihood criteria. This model turned out to be ARMA 4.0 model for the Kaveri monthly stream flows, and we also chose one model corresponding to the minimum mean square error. Now, this model turned out to be the ARMA 1.0 model for the contiguous type of models that yielded the minimum mean square error. Now, once we have identified which model we would like to use for the specific purpose, we need to validate this model. Remember, all of this exercise we did on the first half of the data. We had 480 values, all of this exercise we did only on the first 240 values, except of course, the first part where we identify the periodicities etcetera, where we plot the time series and spectral density and so on. That was done on the entire time series, but once we come to the identification of the model, we focus only on the first half of the data. Now, once we choose the model, we apply this model to the remaining half of the data, in this particular case to the remaining 240 values, and obtain the residuals, and then we do the analysis on the residuals to examine whether the residual series that we so obtain by applying the model chosen to the validation data set. In this particular case, it is 240 values, the remaining 240 values, obtain the residual series, then we do the tests on the residual series for validation. So, typically the validation test will consist of the test to examine whether the residual series has 0 mean or the mean is insignificant, then whether the residuals are devoid of any periodicities, whether there are any periodicities present in the residual series, and whether the residual series that we so obtain is uncorrelated or it constitutes a white noise. So, these are the three types of tests, and I have discussed earlier how we carry out these tests. Today, we will apply these tests to the particular case study that we are considering. Just to recapitulate what models that we chose from for the particular case study, we will just go through this. These are all the details that I have already discussed. Half the data set is used to construct the model and the other half is used for validation. So, this is what I just mentioned, and this is the summary results for the contiguous model. This is the way we calculate the likelihood values. This is the variance of the residuals when we are applying for the calibration period, and that is how we get the likelihood values. You choose that particular model which gives you the maximum likelihood value. In this particular case, it is ARMA 4.0. Similarly, for the non-contiguous models, this is what I have discussed in the last lecture. So, let me go a bit fast. So, ARMA 5.0 turns out to be the best model in terms of the likelihood values. Now, in the contiguous models, if you recall, the last term we included as the 12th lag. So, the last AR and MA terms correspond to the 12th lag. This I have explained in the previous lecture. Now, what we will do is, another minor point here, that when we did all this exercise, the parameters of these models would have been estimated. So, finally, for the chosen model, we give you the parameters phi 1, phi 2, phi 3, phi 4. This is ARMA 4.0 model. It is also typically written as AR 4. When MA term is absent, we simply write it as AR 4 model, and this is a constant term. Now, similarly, for forecasting model, we chose the minimum mean square, the model that gives you the minimum mean square error. In this particular case, it was ARMA 10 or AR1 model. And for the non-contiguous model, it comes out to be ARMA 20 model. Again, the second term in this particular case will correspond to the 12th lag. So, ARMA 20 model for the non-contiguous model will be x t is equal to phi 1 x t minus 1 plus phi 2 x t minus 12. The 12th lag is considered here for forecasting model. Now, both of these yield the same almost the same mean square error value. So, you can use one of the two, and then as I said, we use that particular model which has lower number of parameters. In this particular case, it will be ARMA 10 model. So, these are some of the details. So, for the ARMA 10 model, we again give the parameters phi 1 0.2557 and C is minus 0.009. Remember that we are applying these models to the standardized series, and that is why you get these kind of magnitudes. All right. Now, we will go to the validation tests. So, as I mentioned, we have calibrated the model based on the first half of the data. Now, we will apply these models complete with their parameters to the second half of the model. What do I mean by that? Let us say 240 values. First 240 values you have used to calibrate the model, and therefore, the parameters have been estimated, the models have been fixed. This model we start applying for the next 240 values. So, we generate, as I mentioned, as I discussed in the last perhaps lecture number 18, we generate the data for the next 240 values and then compute the residuals. How do I compute the residuals? This is E t is equal to x t, we have the data, minus this is how the model has simulated. You know the phi j's, you know the theta j's, and similar to this we calculate the estimated value for x t based on the number of parameters that you are using. For AR4 model, we would have 4 models. So, 4 AR parameters. So, it goes from j is equal to 1 to 4, and we do not have any MA parameters. So, this summation we do not consider, plus there is a constant term which we have estimated earlier. So, this is from the simulation from the model. So, this is the simulated data, this is the actual available data, and that is how we calculate the residual. So, we now form the residual series by using this expression. On the residual series, the validation tests are done. First, we examine whether the residual series that we so obtain has a 0 mean or the mean is not significant. Then we also examine whether there are any significant periodicities that are present in the residual series. For the significance periodicities, we also do the Bartlett's test. This Bartlett's test is also for significance of periodicities. Then we examine whether the residual series in fact is uncorrelated. For that, we generally do two tests, Whittle's test and Portmanteau test. Remember that I have mentioned Whittle's test is preferred over the Portmanteau test. Okay, for the case study, we will see now what kind of test that we do. First is the significance of residual mean. If you recall, we formulate the statistic eta as n to the power half E bar by rho cap to the power half. The rho cap is the residual variance. Remember here, the moment you compute the residual series, first obtain the variance as well as the mean of the residuals. Simply obtain the mean and variance. These will be useful for any of the statistical tests that we are doing on the residual series. So, E bar is the residual mean and rho cap is the residual variance. N is the number of data. Now, in this particular case, n will be 240 and E bar is the residual variance, residual mean, and rho cap is the residual variance. Therefore, you can get eta E which is the statistic. These are the values. Although we have chosen a particular model, typically you can do these tests only for the particular chosen model, but just for completeness sake I am giving you for all the candidate models that we have considered these data for all the candidate models. So, these are the type of statistic values that you get. Now, the model passes the test for significance of residual mean. By passing I mean that the residual mean is insignificant, or we can approximate the residual mean to be 0. That is what I mean by the model test passes the test. If the eta value that is so obtained is less than, let us say you are fixing the 95% confidence limit. So, t 0.95 comma 240 minus 1, this 240 is the n that we are considering. So, n minus 1, 0.95 n minus 1, this can be either 0.95 or 0.99, typically we consider 95% confidence level. So, as you can see, this value remains constant because it only depends on the confidence limit and the n value, both of which are constant. So, this is 1.645. If the statistic that you calculate is less than this particular value, then the particular model passes the test. As you can see, all of these values are less than the associated t value, and therefore, all the models pass the test. Although we are interested in this particular model ARMA 40, ARMA 40 is the model that we have chosen that passes the test, but typically you can do this test for all the candidate models just as an exercise. All right, now we will go to significance of periodicity. So, this is the order in which we carry out the test. Typically, first you test for the residual mean, make sure that the residual mean is significant, it is non-significant in the sense that it can be approximated to be 0. Once you are satisfied that the residual mean is 0 or can be approximated to be 0, then you go to significance of periodicities. Why we did this for all the models is, let us say that the chosen model ARMA 40 did not pass the test. Then you go to your again likelihood values, see which is the next best model, then look for that particular model. Let us say that after ARMA 40 you had let us look at which is the other model that you had for see this was 30.85, the next value seems to be 29.81, which is ARMA 22. Let us say that this model did not pass one of the tests, then you go to the next model, next available model in terms of the likelihood values, see whether that model passes the test. That is why we calculate this t statistic as well as the likelihood values for all the candidate models. So, in this particular case ARMA 40 model passes the test, and therefore, we progress further. Once we are satisfied that the residual mean passes the test for its significance, in fact, the lack of significance, then we go to the next test, which is significance of periodicity. Again we formulate a statistic. This statistic is gamma k square n minus 2 by 4 rho 1 cap. Rho 1 cap is now not the residual variance now. In this particular case, rho 1 cap is the corresponding to the periodicity with which we are for which we are testing. We compute the rho 1 cap like this. Remember, omega k is the omega value for the particular periodicity. Let us say we are testing for periodicity number 1, in which in our case it is periodicity of 12 months. Then omega k is that particular value of the periodicity. To make it more clear, let us say that we had our original spectrum like this, and this is the omega k corresponding to the first periodicity, omega k corresponding to the second periodicity, etc. So, this test that we are just discussing now is carried out for one periodicity at a time. So, you pick up the first periodicity, examine whether that periodicity is still present in the residual series, then go to the next periodicity, examine whether that is still present in the residual series, and so on. So, like this, one after the other you carry out the periodicities significance, I am sorry, one after the other you carry out the tests for the periodicities. So, this is for that particular k. So, you can calculate gamma k, where alpha k is given by this and beta k is given by this. Omega k is known, therefore, and E t is the residual series. T is equal to 1 to n, and n is in this particular case 240, and alpha k and beta k are obtained from here. So, this is alpha k corresponding to that particular k, and similarly this is beta k corresponding to that particular k. Remember here t is the time period. So, this is going from 1 to n, and the small n and capital N are analogous, they are the same n, in this case it is 240. So, you can get gamma k square. Once you know gamma k square and rho 1 cap is estimated like this, you can get eta because you know n. So, eta is obtained like this. 2 pi by omega k is the periodicity for which the test is being carried out. Let us say you are testing for 12 months, then you can obtain the associated omega k. This is typically obtained from your spectral analysis. Now, if this statistic value that you calculate is less than the f alpha to n minus 2, then it passes the test. 2 is the degrees of freedom and n minus 2 is n is the number of data, in this case it is again 240. Alpha is the significance level, typically we use 95% value corresponding to this. So, we do this significance of periodicity test on all the models, all the candidate models. The first periodicity is 12 months, second is 6, third is 4 and fourth is 3 months. Associated with those particular omega k values, we calculate these statistic values. Remember again that these are all done for the residual series. So, on the residual series we calculate these eta values, and the associated f statistic value, which is a critical value, is 2,238, n is 240. So, this becomes 238 and this is a 95% significance value. These values of f 0.95 can be picked up from any standard tables of the f distribution. Any of the standard textbooks will provide this f value associated with the degrees of freedom and n minus 2, and that comes out to be 3. As you can see, all the models pass the test for all the periodicities, indicating that none of these periodicities is significant in the residual series. We have done the tests of periodicities one at a time. So, first we consider the first periodicity, which is corresponding to 12 months, next 6 months, 4 months and 3 months, and we conclude that all the models pass the test. But as I discussed in the one of the earlier lectures, maybe lecture number 17 or 18, that instead of doing the tests on periodicities one at a time, we would prefer to test all the periodicities at a time. That means, we have the residual series available with us now. With this residual series, can we examine whether there is any significant periodicity present at all in the residual series. Now, this is best achieved by the Bartlett's test or the cumulative periodogram test. Now, the cumulative periodogram test, which I will discuss now, will apply to case study number 3, which is Kaveri river flows. If you recall, in the Bartlett's test, what we do, again we formulate gamma k square, which is 2 by n E t cos omega k t plus 2 by n E t sin summation sin omega t whole square. So, this is gamma k square. This we do for k is equal to 1, 2 etcetera n by 2. Then we calculate the cumulative periodogram G k is equal to by considering G k is equal to gamma j square, j is equal to 1 to k, let us say k is equal to 2, this goes from 1 to 2 divided by gamma k square, k is equal to 1 to n by 2, the whole range. So, this is normalized gamma j square. So, G k is what we require for constructing the periodogram. So, G k versus k, the plot of G k versus k is called as the cumulative periodogram. So, you know how to calculate gamma k for a given k, and you know now how to calculate G k. So, from this now let us say that we calculated the G k for the original time series. That means, the original all the 480 values, monthly values, we compute G k and then plot for lag k versus G k. Typically, we go up to n by 2, lag k we go up to n by 2. In this particular case, it is 480 by 2, which is 240. Then what we do is the point 0 0 here and n by 2 and 1. So, G k the maximum value is 1. So, n by 2 in this particular case is 240. So, 240 and 1, we join that those two particular points by a line. Around this line we form the confidence bands. Now, this confidence band, if you recall, is 1.35 by n by the root n by 2. This 1.35 corresponds to 95% value. So, 95% confidence value is 1.35 by root n by 2. This comes out to be 0.087. Now, this 0.087 we draw a line at each of these points and form a band. Now, this gives you the band of confidence for this particular test. On either side we draw that line, and as you can see, for the original monthly time series where we had 480 values, if you conduct this test for the original time series, you see that most of the values lie above this band, beyond this band, indicating that there are significant periodicities present. In fact, you see a first spike corresponding to a value of 40. So, 480 by 40, that corresponds to a periodicity of 12 months. Similarly, you can capture periodicities associated with each of the spikes. So, this is cumulative periodogram. Now, the same test we carry out on the residual. Remember, this test that I just mentioned now, this cumulative periodogram is not a test on the residuals. I am just showing this to indicate that if you have periodicities, this is how the cumulative periodogram will appear, whereas you do not want any periodicities to be present in the residual series. So, we do the test on the residual series and look at for the ARMA 4.0 model, how does the cumulative periodogram look like. Now, we now consider 240 values, because we are calculating the residual on the remaining half, which is on half of the data, which is 240. So, the number of values that we consider for lag k is n by 2, which is 240 by 2, which is 120. So, from 120 to 1 and 0 0, you draw this line, and around this line you form the confidence limit. How do we get the confidence limit now? 1.35 by root n by 2, and n in this case is 240, and therefore, you get a band of plus minus 0.123. By plus minus I mean it is on either side of this particular line, red line that is drawn here. Then we form the cumulative periodogram. How do we get the cumulative periodogram? We apply this now on the residual series. So, you get G k on the residual series and G k versus k on the residual series. This is the plot of the cumulative periodogram. This dark blue line, black line shows the cumulative periodogram. If the entire cumulative periodogram lies within this confidence band, then there are no significant periodicities present in the data. As you can see, the cumulative periodogram in this particular case of the residual series lies completely within the confidence band, and therefore, there are no significant periodicities present in the data, and therefore, the residual series corresponding to ARMA 40 model passes the test for periodicities. When I say it passes the test for periodicities, it means that there are no significant periodicities present in the residual series. We conducted 2 tests for the examination for testing whether there are periodicities present, whether there are significant periodicities present in the residual series or not. Among the 2 tests, this particular test, which is called as the Bartlett's test or the cumulative periodogram test, is preferred because you can do the test in one go for all the periodicities, whereas in the earlier case we did one periodicity at a time. You do the test for the first periodicity, remove that periodicity from the data, then do for the next one, remove that periodicity if it is significant, and then go to the next one, and so on. So, you did one at a time in the earlier case, whereas in the cumulative periodogram test, you simply plot the cumulative periodogram, you draw the confidence limits, the band of confidence limits, and then for all the periodicities at a single time, you can examine whether the model passes the test or not. So, this test is preferred over the earlier test. We now examined for the significance of mean. We satisfied ourselves that the model that is chosen ARMA 40 does not have a significant mean, the residuals resulting from that residual series does not have significant mean, which means that the mean is 0, mean can be approximated to be 0. We also satisfied ourselves that there are no significant periodicities present in the data, present in the residual series by doing the cumulative periodogram test and the test that I just discussed earlier. Now, we have to look at the another important assumption that we made in building the model, that the residual series is uncorrelated. This is also called as the test for white noise. That means, the residual series that we obtain from applying the model should be should constitute a white noise in terms of absence of any correlations in the residual series. So, this is what we do by 2 tests, Whittle's test and Portmanteau test, both of which require the covariance matrix of the residual series. So, once we constitute the residual series, we form the covariance matrix of the residual series. Now, based on the covariance matrix, we define a statistic for the Whittle's test and a different statistic for the Portmanteau test, and then based on this statistic we formulate based on the covariance matrix, we examine whether the series is in fact uncorrelated. So, let us see what is the Whittle's test. This I have discussed earlier, but just to recapitulate, essentially what we do is we formulate the covariance rho k, the covariance R k at lag k of the error series E t, error or residual series is the same. So, this we go from k is equal to 0, 1, 2 etcetera k max. We typically consider the maximum k as 0.15 n. N is the number of data points, in this particular case it will be 240. So, the covariance is taken as E j minus k. Remember how did we define covariance? X t minus mu into that is the expected value of x t minus mu into expected value of x t minus k minus mu. So, this was your R k for the original time series x t. but because we have verified that the mean of the residual series is in fact 0. So, I write the covariance as R k is equal to 1 by n minus k E j into E j minus k, because the residual mean is 0 and j goes from k plus 1 to n. So, k is, let us say you are calculating for 2, k is equal to 2, you will have n minus 2 here, n is 240 and this goes from 3 to n, which is 240, and typically we calculate this for up to k max, and k max is typically taken as 0.15 n, and I am going through the textbook Kashyap and Rao dynamic stochastic models from empirical data. Just as a aside, I would like to mention that Professor Kashyap is an electrical engineer and has contributed significantly to stochastic models, to the theory of stochastic models, and Professor Ramchandra Rao is a civil engineer, he is a hydrologist. Both of them were at Purdue University and have contributed significantly through this particular classical textbook, dynamic stochastic models from empirical data. There are large number of examples from the electrical engineering, and there are also significant number of examples from hydrology in this particular textbook. I would encourage all of you to have a look at this particular textbook. All right, now you have formulated the covariance. Now, once you have the covariance matrix, this is gamma n 1, you have the entire covariance matrix k max into k max size. We formulate gamma n 1 minus 1 by taking out the last row and the last column. So, you have gamma n 1 as complete covariance matrix of size k max by k max. Then you take out the last row and the last column to formulate gamma n 1 minus 1. Then we define the statistic eta e as n divided by n 1 minus 1, where n 1 is the k max, into rho naught cap by rho 1 cap minus 1, where rho naught cap is a lag 0 correlation, which is 1, and rho 1 cap is determinant gamma n 1. This is gamma n 1, you take the determinant of this by determinant gamma n 1 minus 1. As I said, gamma n 1 minus 1 is formulated by taking out the last row and the last column. So, the matrix gamma n 1 minus 1 is constructed by eliminating the last row and the last column from the gamma n 1 matrix. So, you can get rho 1 cap. Once you get rho 1 cap, you know rho naught cap, which is 1, and you know n 1, which is k max, typically 0.15 into n. You know n, which is 240 in this particular case, and therefore, you will get eta. Once you get eta, you compare this eta with f alpha n 1 n minus n 1. N 1 is a in this particular case it is k max, that defines the degrees of freedom, and n minus n 1. If the eta you have calculated is less than this critical value of f, and alpha is typically chosen as 0.95 or something, then it passes the test. So, for the case study now, let us carry out the Whittle's test. So, you know how to formulate n now. I have not given all the data details of the covariance matrix and so on. I leave it as an exercise for you. I will give you the final results here. So, the final results for the Whittle's test, we do it for all the candidate models, although we can do it only for the particular model that we have chosen, namely ARMA 40. You could have done only for ARMA 40, but as a not necessarily only as an exercise, but as I mentioned, you do it for all the candidate models, so that if the particular model that you have chosen does not pass the test, then you can go to another model. So, typically we do this test for all the candidate models that we have chosen. Now, we consider N1 variously as 73, 49, 25 and so on. So, you can do it for several N1s. Typically, you can choose it up to 0.15 N. In our case, N was 240. We have considered half the data. So, you could have gone up to 0.15 N. So, you consider for various tests just to see where does the model fail. So, as you can see, these are the eta values that you obtain for different N1 values. So, let us say N1 is equal to 73, I take like this. Then corresponding to that particular N1, you will have f 0.95 and 239, 239 being n minus n1. I am sorry, there is a mistake here. This is not f 0.95 to 39. So, this is what you get from the table. This is actually what I have written here, that is f alpha n 1 n minus n 1. So, this is f alpha n 1 comma n minus n 1. So, these are the values that you get 1.29, 1.39 and 1.52. If these values that you are getting of the statistic are less than the particular f alpha values, then the model passes the test. As you can see, most of the models pass the test, but when you come to ARMA 1-2 model here 1.581, which is more than 1.52 for both ARMA 1-2 as well as ARMA 2-1 models, these models fail the test, whereas all other models pass the test, and we are concerned with ARMA 4-0 model which passes the test. So, this is the white noise test to examine whether the residual series E t that we have constitutes a white noise in as much as the correlations are all insignificant. That means, there is no significant correlation present in the data. That is the Whittle's test, which is to examine whether the series constitutes a white noise. We have another test which is called as a Portmanteau test, which again uses R k, which is a covariance matrix. We go from k is equal to 1 to n 1. This is simply R k by R naught, which is rho k, if you recall. R k is the covariance at lag k, and R naught is covariance at lag 0, which is the variance itself, and k is equal to 1 to n 1. N 1 is the maximum lag. N 1 and k max are similar. Now, this test uses the chi-square value, the statistic eta e follows chi-square distribution. So, at 95% significance value with k max as argument, you get the critical values of chi-square as 65, 50.8, 36.0 and 21.0 for various values of k max that I have considered. And the eta values that you are obtaining here, n is 240, n 1 is the k max here. So, for this it is 48, for this 36 and so on. So, you can get eta values. The eta values here must be less than the associated chi-square value for this to pass the Portmanteau test. And in this case, for k max is equal to 48, all of them pass the test, and this is 2 of them fail the test, and again 2 of them fail the test. So, ARMA 1-2 and ARMA 2-1 fail the test for lower values of k max, and all other models pass the test. Again, between Portmanteau and Whittle's test, we prefer the Whittle's test. That means, suppose there are conflicting results between Portmanteau test and the Whittle's test, then you go with the results of the Whittle's test. All right. So, that completes the case study number 3, which is on monthly stream flows for Kaveri river at KRS reservoir. Let me just quickly recapitulate what all we did for case study number 3, because this is the most extensive case study that I would discuss in this particular class, particular course. All the other case studies that I will discuss subsequently, we will simply summarize what kind of tests we do and so on, simply summarize the results. So, in the case study 3, our aim was to finally build a model, time series model for the monthly time series, both for long term simulation of the data, long term synthetic generation of the data, as well as for short term forecasting, one time step ahead forecasting. So, we built the model by considering a number of candidate models. We estimated the parameters by taking half the data, and then we did the tests by constructing the residual series by applying the candidate models to the remaining half of the data. Corresponding to each of these residual series, we did the tests based on we did the tests to examine whether the residual series has a 0 mean, whether it is devoid of periodicities, all the periodicities are removed, and whether the residual series is uncorrelated. So, these 3 tests we did, and then finally chose ARMA 4.0 model for synthetic generation and ARMA 1.0 model for forecasting of the data. Now, similar case studies I will discuss now, but we will not spend as much time as we did on the first case study. Just to give you a variety of the time series that we come across in hydrology. Next, again we will take a monthly stream flow, but not in the monsoon region. See, the Kaveri river typically comes in the peninsular region of the country of India, where it is essentially driven by the monsoon patterns. So, the monsoon flows contribute to the Kaveri river. So, it behaved in a particular manner. So, we chose those particular type of models. Now, I am taking a stream flow data. This is taken from one of the US rivers, and the data is directly downloaded from the USGS site, and this is the monthly data from 1928 to 1964. 37 years of monthly data is available. So, about 444 values are there. So, this is how the time series looks. You can compare the time series of this type of stream flow with any other Indian rivers that we consider. Maybe you can compare it with the Kaveri river and so on. So, you will see the type of differences that you may get. Then we construct the correlogram. Correlogram shows periodicity, but there are significant there are a large number of periodicities which are insignificant. As you can see, these are the bands of 2 by root n on either side, that is plus minus 2 by root n. As you can see, mostly only the positive correlations are significant, most of the negative correlations are insignificant in this particular case. Although this does indicate that there are periodicities present here. Then we do the spectral analysis, the partial autocorrelations. The partial autocorrelations, again there are certain partial autocorrelations significant here. The first one is significant, and similarly there are several of them significant. The autocorrelogram also shows that there is a decay, there is a slow decay in the autocorrelations, and the partial autocorrelations show up some significant partial autocorrelations, which means that if you are building a AAR model, you can pick up these partial autocorrelations and then pick those particular terms. The spectral density again shows there are certain periodicities. This corresponds to a periodicity of 6 months. There is no periodicity that is shown at 12 months here, corresponding to 0.54 or some such thing, as we saw in the case of Kaveri. There is no significant periodicity here. However, there is a periodicity corresponding to 6 months, and then perhaps corresponding to 3 months and so on. So, it does show that there are periodicities present. Then we go on to build a large number of candidate models ARMA 10 etc., it goes on up to ARMA 80, and then typically we take up to 1 and 2 of the MA terms and 1 and 2 of the MA terms. So, these are purely moving average models. These are ARMA models where you have both AR as well as MA terms. Here you have only AR terms, and we compute the parameters. We estimate the parameters here phi 1 to phi 8 and theta 1 and theta 2. So, for ARMA 80 model you have all the 8 AR parameters, but no MA parameters here. So, similarly you get all the parameters corresponding to AR and MA terms here. Once we calibrate the models based on half the data, we then calculate both the mean square error as well as both the mean square error as well as the likelihood value. This is the log likelihood value. As you can see here, the ARMA 80 model turns out to be the best both in terms of the mean square error as well as in terms of the likelihood value, much unlike what we saw in the Kaveri river data. Kaveri river data we got ARMA 40 for synthetic generation, whereas ARMA 10 for our short term forecasting. Whereas, in this particular case, which is a US stream, you get ARMA 80 as the best model both for synthetic generation as well as for short term one time step ahead forecasting. Then we do the residual test, that is tests for on the residual series. So, first we check whether the mean is significant. We formulate this statistic eta e and then compare it with the T alpha n minus 1. In this case n is about n is exactly 444, 37 years of values, and then you get eta e values which are very small compared to the n value. They typically come e to the power minus 5 and so on. So, this passes the test. All the models pass the test, and typically we are interested in ARMA 80. ARMA 80 passes the test, indicating that the residuals do not have a significant mean, or the mean of the residuals can be approximated to be 0. Similarly, we do all the tests. I am not indicating all the details of other tests. You can do it as an exercise, and then you satisfy that all the tests are passed. I am sorry, I am not giving you the data. So, you will not be able to do those tests yourself. So, I am indicating here that similar to the residual mean, we do the test that I just discussed for the Kaveri case study, and then ensure that all the models, the model that we have chosen, namely ARMA 80, passes all the tests. Now, this is another type of time series that we are considering. The first one, which is case study number 3, we considered the Kaveri river flows, which are essentially driven by the monsoon flows, monsoon pattern, and that is monthly time series. Then we went to another monthly stream flow time series, where we considered a western river, that is a river in the US, and then we did the example of fitting the time series. We came up with a model of ARMA 80 or AR 80, AR 8. Now, we look at another type of time series, which is Sakleshpur annual rainfall data. Sakleshpur is in the western Ghats of the nation of India, western Ghats. Typically, the monsoon patterns here are much different compared to any other region in the country. So, we consider this annual rainfall data. So, the annual rainfall data in the Sakleshpur region for 1901 to 2002, 102 years of data is available. So, you see the time series. Remember, this is annual data. So, you are not getting any, you are not seeing any particular pattern here. So, you get the time series plot like this, and then we look at the partial autocorrelation. This is autocorrelation ACF and the partial autocorrelation, and then we go on to build the models and then look at the type of models that we get. for synthetic generation as well as one time step ahead forecasting. As I discussed earlier in one of the earlier lectures, annual rainfall can be modeled as using one of these ARMA type of models, if we are satisfied that if we transform it to make sure that there is no stationarity, there is no non-stationarity present in the data. Whereas, if you go down on time scales, let us say that from annual you come to monthly rainfall, then from monthly you come to daily rainfall, etc. There are significant non-stationarities that will be present, which are not easily removed even if you do say differencing. Typically on the daily rainfall data, let us say even if you do the first order differencing, second order differencing, etc., the non-stationarities will still remain. So, when you want to apply the ARMA type of models, first you must make sure that you have transformed the original time series to another time series which is stationary. These models are only for stationary time series. So, the case study number 5 which I am dealing with is annual rainfall series in a high intensity rainfall region, namely the Western Ghats region of India. We will see how this behaves when we apply the time series models. We will continue this discussion in the next lecture. So, essentially I have dealt with today mainly two case studies. Case study number 3 which I started in the last lecture, and we completed the case study number 3 in some detail, where I explained all the tests that we do on the residual series. Then we quickly ran through another case study number 4, which is a monthly stream flow time series of a US river, United States river, which the data can be downloaded from the USGS site. And then we have just introduced another case study. We have just looked at the annual time series, annual rainfall time series of Sakleshpur data. This case study I will continue discussion on this particular case study in the next lecture. So, thank you for your attention. We will continue the discussion in the next lecture.